Hello everyone, again welcome back to the latest lecture session. Again a very quick recap of what we have been up to. So we are discussing remediation of groundwater contaminated with uranium, and we are looking at a particular case study from I think Utah, or in Utah rather, right? And I think they had what do we say, ore processing or upgrading facility, and among other heavy metals they had, let's say, radioactive what do we say, material, uranium too, I guess, right? And in that context we are looking at PRB, and what have we looked at thus far? We looked at the relevant batch tests, let's say, or some information regarding batch tests, and then moved on to the relevant data from the column tests, right? So this is data obviously you need to have to be able to design your thickness of your particular PRB, right? And that's something we have looked at. You can get the rate constant or such, or the pseudo rate constant for the relevant removal of these compounds. You also can get the extent of removal or the maximum extent that you can expect, and obviously you can also look at the desorption studies for some of these relevant compounds, and we looked at that data, right? And so then we moved on to the relevant aspects, as in we looked at what are the factors that we consider in evaluating the materials. So a quick recap of them. So obviously availability, and I believe cost, right? So permeable than the surrounding aquifer, so that's one particular aspect. As in with respect to the phosphate materials, we saw that what do we say, based on the way we look at it or analyze it, as in the uranium concentration per gram of phosphate material or uranium concentration per area of phosphate material, the performance seems to differ, right? But obviously we can't just look at only surface area, obviously, because we have issues with respect to the amount of what do we say, the PRB material you can put in. And also, let's say, way too smaller size, you are going to have issues with permeability, right? So that's something to keep in mind. And again, structural strength, obviously, right? Because you want to, depending upon the depth to which you are going to place the PRB, right? You need to have resistance to compactive crushing, and then extent, rate, and duration of uranium removal. That's something you'll get from the column and batch tests, right? And mobility, right? As in the relevant PRB material should not be mobile, let's say, or should not be made more mobile once it interacts with the relevant contaminant, right? And potential for desorption or release of uranium once the uncontaminated groundwater comes in contact with your PRB, that's something else. And then obviously you are going to have issues with respect to pH change or iron and phosphate release, because that's what we are looking at. As in the case of zero valent iron, what do we have? Fe0 going to Fe2 plus or 3 plus, right? So Fe2 plus is released, but obviously you don't want to have way too high concentrations of iron in the water. You will have the relevant standards for that particular compound too, or iron too, right? So these were the aspects we looked at. So let's just try to look at some of the summarized data here. So both batch and column uptake text indicate that what now? So if you look at the data, or you can remember the data, the bone meal and bone charcoal did pretty well on a per gram basis, right? And because of its small particle size, bone charcoal powder suffered from the need to dilute with coarse material, because looks like the size was too small, and thus permeability issues. So it had to be diluted with coarse material and then again transported, otherwise it would or maybe transported out of the PRB. And also the hydraulic conductivity of the pelletized bone char phosphate, right, what would that or how is that useful? Because now you don't need to add any other, what we say, relatively more porous material or such, because the hydraulic conductivity of the relevant pelletized bone char phosphate is high enough, obviously, that it can be used in the PRB without dilution, right? Again, these were mostly with respect to the bone char or the phosphate materials, but based on the relevant aspects, and some of the data we looked at, these were the finally chosen compounds, right? Finally chosen compounds. Again, what were the three processes? One, with respect to phosphate, it was just precipitation, uranyl phosphate phase, I guess, right? For that, obviously, you need calcium and such, what do we say, cations too, right? And we also looked at zero valent iron, but the process was that first reduction from +6 to +4. So thus you need to provide a source of electrons. Where are the electrons coming from? Obviously from your reducing agent, which is the zero valent iron, right? And then for the precipitation, and then the third mode, which is just adsorption, not just, let's say, adsorption, and the adsorbent was the ferric oxyhydroxide, I guess, right? So based on the relevant test, they chose what do we say, one material for each of these three kinds of process that we talked about. These are the finally chosen what do we say, compounds, and here you see the actual placement of the relevant PRB, as in out here you can see that out here in the PRB, right. And now the key aspect is to understand, let us say that the contours of the relevant what do we say, groundwater, or the potentiometric contours change too, right. If you can bring up the relevant contours before installation of the PRB and compare it to what we have here, you would see that the contours would change in this particular zone, or the capture zone. Obviously this I think is supposed to be the approximate capture zone, right. And I think we had uranium tailings somewhere out here, if I am not wrong. And obviously as you see, this is the channel or the stream, Fry Creek, let us say the Fry Creek channel. So earlier the groundwater was, this contaminated groundwater was flowing into the stream here, and so again thus depending upon this particular groundwater flow and the prospect of further transport of the contaminant, they place the relevant PRB here, and so that is what you have here. And I guess they have the different control points, right, before, after, and inside the relevant PRB, right. So that is something that you see here. And again here we have the top view here, right, top view I guess, yes. So here we have the wing wall. Again, what is this system though? It is funnel and gate, obviously not, it is funnel and gate system, obviously not the continuous. So here you can see the wing here, right. So you can see the wing here, yes, and 3 PRB materials were placed here in series now, right. So where are they? This is the wing out here, and so here we have AFO, the ferric oxyhydroxide or ferric hydroxide, and here we have 0 valent iron, and here we have the 0 bone char phosphate and another wing wall out here, I guess, right. So what did they have here? So they had gravel here, that is relatively more porous and high hydraulic conductivity. Obviously you want to have groundwater flow in this particular direction, and they had fill, let us say impermeable layers I guess between this PRB material, and now obviously the groundwater will flow through the AFO, right, through the ZVI and through the bone charcoal, let us say, right. And this is what we have out here, this is the setup anyway. So again impermeable wall out here, that is something that you can see. Obviously you do not want to have the groundwater flowing around the particular system, right. You have the impermeable wall, and typical groundwater flow direction, as they say, is in this direction. As you can see from the contours too, I guess they say it is in this direction, right. So keep in mind that because of the what do we say, placement of the type of placement of the PRB, the groundwater table might not be uniform across the 3 types of the PRB, let's say, right. And also keep in mind that the contours change pretty rapidly here, let's say, or the gradient is pretty steep here. And why is that? Because we have a stream nearby, that is obviously one particular case. So obviously this is the side view from here, side view. What do we have here? We have the fill here, this is the what do we say, soil surface here, and then I guess the fill, and this is the PRB material. So 1.5 feet thick gravel, that is what we see here, and this is your PRB material, and looks like they designed it for 3 feet, right. And in this AFO the groundwater is at 2.4 feet approximately, and obviously the fill and such will be the same for 0 valent iron and bone char phosphate. But looks like the groundwater table seems to be as you can see, it is not uniform out here, right. Again the fill here, but here the height of the PRB2 is greater, as you see. But keep in mind, for comparative analysis you will have to have similar thickness of the PRB, and that is something you see 3 feet, 3 feet, 3 feet. But because of the differing height of this particular contaminated groundwater, you have different, what do we say, heights of the AFO. 0 valent iron seems to be 4 feet, and bone char seems to be around, okay, they have the relevant what do we say, 4 feet is the height of the table, I guess, groundwater table, pardon me, right, from the base of that particular PRB. They did keep the height the same, the 3.2 feet, 3.7 approximately here, and 3.2 feet, right. But again, if you are actually designing it for the complete removal, you will have to have your PRB extending to such a height that it can cover the entire contaminated plume. But again, this is for field analysis to see whether it works or not and how does it work and such, right. So this is what we have out here, and let's move on. Obviously here we have the placement of the AFO barrier material. So for that, obviously you need to also design for this sacrificial frame. I think I have pictured. I think this is where they were putting the barrier material, or I think this is the fill, right. And here this is the sacrificial frame, and again design for that. But obviously the design of this sacrificial frame anyway is outside our purview, but just to be able to understand, I guess I'm providing this particular graphic. Again, as I mentioned, all those particular graphs that I have are not the data that I source, but from the relevant reference that I presented in a couple of sessions ago, right. So that's something to keep in mind, and that's available in the public domain. So here it's the top view in greater detail, obviously, and here we are looking at it with respect to the zero valent iron PRB, right. As we looked at it earlier, let's say, what do we have here? We have 1.5 feet thick gravel, which is this, obviously, right. 1.5 feet thick gravel, and that's what you see out here, 1.5 feet thick. And obviously they have a monitoring well within that particular gravel to obviously look at what is the concentration of the contaminant coming, or the influent concentration of the contaminant, right. And then they have monitoring wells, different kinds, as in 2 sampling depths, 1 sampling depth, right, 1 sampling depth and 2 sampling depths. So different kinds of monitoring wells inside the PRB, right. Inside the PRB you have 2 rows of them, row 1 and row 2, right. And again, barrier material, obviously all this is zero valent iron, right, all this is zero valent iron, and you have different sensors here again, yes, and 2 feet from the sides, that's the placement of the relevant rows. This is with respect to zero valent iron. And for this particular same case, more or less with respect to the AFO PRB, right, more or less, right. Again, they have what we say monitoring wells or ports outside, or after the exit of the relevant PRB, and here let's say to be able to understand the what we say actual case of, or what are the advantages of PRB, as we discussed them earlier. One aspect is that above ground structures are remarkably minimal, and so what do we see here? This is all the above ground structure that you have for your particular PRB for, I think, maybe zero valent iron or AFO though, right. So this is a 2-inch monitoring well, okay. So this is the only structure, and again workers during the installation, I guess, different depths and so on. But keep in mind that one of the obvious advantages of PRB is that we are going to have relatively little, what do we say, above the surface structures, right, or not little, pardon me, less number of above ground structures. So typically, you can either, not either, let's say, have somebody come in and take the readings manually. Typically you will have the automatic data loggers, that's what you see here. So AFO, zero valent iron and bone char, right. We have saw the relevant what do we say data loggers, not data loggers, I guess, the ports for data gathering, I guess, if I can call them, and they are connected to this mobile laboratory, let's say, and data logger, automatic data logger, and they have the solar mounted panels and such. So again, key aspect is what is it that we have? We are just collecting the data automatically, and we obviously don't need to have any regular or continuous monitoring, obviously. So from time to time, let's say somebody remotely can look at this particular data, or analyze that from time to time. Obviously there is no need for continuous monitoring or such though, continuous manual monitoring anyway, right. So again, what do we have here? What are the results that we have had, or let's look at that. So uranium removed in PO4 3- or the phosphate in AFO PRBs was more than 70%, right, and they looked at it for 1 year, and this is in line with what we saw in the particular column test and such. So this is the data from the actual placement of the relevant what do we say PRBs, right. But as you can see, again, as expected from the relevant column test, the zero valent iron PRB has lowered the input concentration by more than 99.9% for more or less the whole year though. Obviously, they have run it since then for greater time, and even for that, I believe for 10 years or so, it worked pretty well. But keep in mind now you can see apparent differences in the performance of the relevant PRBs. So let's look at these aspects in greater detail. So here I have uranium concentration, in microgram per liter, and this is for the PO4 or phosphate relevant PRB. Row 1, as in if you can remember PRB, we had row 1 and row 2 monitoring locations, and again row 2 here. So, cross sectional distance from gravel barrier material interface in feet. So, this is the, so as you go along, this is the distance in the PRB or inside the PRB, right. So, this is the gravel and PRB interface, and as we move along, obviously inside the PRB, let us say I think the thickness was around 3 feet, I guess, right. So, this is more or less the 3 feet relevant thickness, right, the distance. So, same case out here, but I guess here I have the better scale here. So, here is 0 as in here. So, what does this data correspond to? If you remember, we had relevant what do we say, sampling ports before the PRB. So, this gives me an idea about the uranium concentration coming in C naught, let us say, and obviously these are the ports we had 1, 2, 3, 4, 5, I guess, row 1 and row 2, right, and that is what we have out here. Because I have the graph here, let me try to analyze this particular case, right. So, this is the interface here. So, this is the inlet concentration. So, as you see, the concentration at what do we say, a particular, the first set of wells in row 2, let us say, is relatively what do we say, less, but as you can see, it is not 0 for all the what do we say, sample time zones, I guess, as in they started sampling from September 1997 to 1998. So, obviously depending upon the type of flows or groundwater flows, different concentrations were experienced upstream of the relevant PRB. So, that particular removal percentage seems to be obviously well correlated to the influent concentration, right. For if the concentration was relatively high, typically anyway, the performance seems to be differing, let us say, or relatively the performance was relatively poor, and obviously for the relevant relatively low concentrations coming in, you see what do we say, the low concentrations going out. But obviously that is a very generic analysis. We need to look at the relevant data with respect to what kind of model it follows or what is the percentage removal, I guess, right. But keep in mind that the influent concentrations varied widely with season, yes. So, for example, in September 1997 it was 4000 ppb, right, and September 1998, I guess, as you can see, by that time, right, the concentration relatively decreased. What does that mean? I guess one of the factors is that maybe the contaminated plume has more or less been attenuated, right. That is what you see here. So, let us look at that data briefly. Again, all of them are bunched together here, so that is not a great deal to understand, but one aspect is you do not have much further removal as you go further into the PRB. This is the 3 feet of your PRB thickness, right, 3 feet PRB thickness, and you had gravel here, you had gravel. So, as you went along, you did not actually see much better removal or such, and keep in mind that the key aspect here is its precipitation. The process is based on precipitation, right. So, when you look at precipitation and dissolution, you will always have an equilibrium concentration, what do we say, that will be in the water, that will be in equilibrium with the solid phase. For example, if it is only precipitation, you will typically not have what do we say 100% removal, right. Why is that? Because the contaminant is going to be in equilibrium between the aqueous phase and the solid phase, let us say. Probably that is one of the reasons why, probably anyway, with this relatively preliminary data, that you do not observe 100% removal. For example, a simple example is, what am I saying is that CaCO3 solid can dissolve into Ca2 plus and CO3 2 minus, right. So, if I am trying to remove Ca2 plus, let us say, right, and what I am saying is that you will never have 100% or 0 concentration of Ca2 plus in the water. Why is that? Because as you can see, the system will be in equilibrium between the precipitate or the solid phase and the concentration of the relevant compound in the water, right. So, that is something to keep in mind. So, let us move on. So, we are moving on to the second one, which is the zero valent iron barrier, but keep in mind that the influent concentrations for row 1 and row 2 are different. And again, why is that? Obviously, that the plume, what we say, direction, let us say, and also the groundwater level gradient, let us say, or the potentiometric contour gradient, let us say, or the contours, let us say, right, are not uniform. So, let us say, thus you have different concentrations coming in for row 1 and different concentrations coming in for row 2. And also keep in mind, looks like zero valent iron row 1 is experiencing much higher inlet concentrations compared to the phosphate relevant barrier, right. Here the maximum seems to be around 4,800 and 4,000 here, but here the maximum seems to be around 12,500 or 12,000 here, right. So that's something to keep in mind, right. So again we are going to analyze the zero valent iron PRB, right. So this is minus 0.5, this is 0 and this is 0.5, right. And this is the interface out here, and this is the 3 feet thick PRB of zero valent iron. So what do you see here though? You see that almost always we experienced 100% removal, right. So this is the influent concentration, as you can see, observe in the gravel. This is the gravel section and the water is flowing, let us say, in this particular direction, as you can visualize, let us say. And what do we have out here? We see that the influent concentration, irrespective of it being pretty high, other than the first particular data set, let us say in September, all the concentration, let us say all the data sets inside the PRB indicate that almost, let us say, 100% removal, right. Again the mechanism here is that it is reduction and then precipitation, right. And again same profile more or less for row 2, right. So this is the first set of wells, second and third inside the PRB, and these are the inlet concentrations, and you can see that more or less you end up with 100% removal here, right. So that's something to keep in mind. Again here you can obviously see or understand the relatively greater efficiency of removal that you come across in the zero valent iron barrier, right. So here let us look at the percentage of input uranium concentration removed after traveling approximately 1.5 feet into each of the PRBs. So what are we comparing? So here we looked at the thickness was 3 feet. So we are comparing the data at after the water has traveled 1.5 feet into each PRB, and the groundwater is obviously flowing in this direction. Let us say my monitoring well is somewhere out here, right. Groundwater flow is this direction. So PO4 row 1 and row 2, zero valent iron and AFO obviously. Typically, as we looked at the relevant data until now, which particular barrier performed pretty well both in the column test and also this in the field conditions, the zero valent iron, and obviously you see that the removal after just 1.5 feet is almost 100%, right. And typically row 1 did better than row 2, could be due to various factors. Again we haven't looked at that in detail, but again as you see typically I guess same case here, row 1 and row 2, but this is from very generic analysis, but the take home message is, as you can see, the zero valent iron did pretty well, right, both for row 1 and row 2 compared to the other barriers out here, right. And do I see any trends here? I guess I can plot them and look at it, but not great trends here, let us say, I guess, right. And obviously with season, you will have differing conditions of influent groundwater to other parameters or variables, and that will affect them, and obviously we are going to look at some of those aspects. So what do we have here? We have changes in dissolved uranium concentrations in the zero valent iron from September 1997 through September 1998. So the cross section distance from gravel barrier material interface in feet again here. So earlier we looked at the cases for zero valent iron and phosphate, and now I guess we have the case for AFO here, yes. So same case here. Let me look at this data here. Concentrations that this particular AFO is experiencing, as you can see, are remarkably high though, much more higher. So again what was the mechanism here? It was removal by adsorption, right, it is adsorption. Amorphous ferric hydroxide, that is what we have here as our barrier material, and the relevant compound is being adsorbed onto the relevant material here, right. So typically as you see, what do you see here? Relatively high concentrations out here in the gravel, and this is the interface between the barrier and the PRB. Again the groundwater is flowing in this direction, and you see some removal, not a lot, but as it moves through it, as in groundwater moves through the relevant adsorbent, you obviously see greater removal, right. That is something obviously you would expect, right. So it comes in contact, it as in the contaminant comes in contact with the adsorbent material, and as it passes through the PRB, or you can visualize it as a column, you have greater removal along the length of the relevant column or the thickness of the PRB. So that is what you see here, right. and that is what you see out here. Yes, so that is something to keep in mind, but that is more apparent in row 2 than in row 1 though. Yes, so let us go ahead. So one of the aspects we mentioned earlier was that we need to look at variation in pH and obviously percentage uranium, and looks like there was a trend here, but people could not come up with a worthwhile way to be able to explain this particular aspect. But let us look at these aspects, as in these are some of the aspects that people should understand, try to understand later. So on the y axis we have pH, on the x axis we have uranium removal on the other axis here, and the sampling date on the x axis. But the trend here you see is that as the uranium pH increased, let us say the pH increased, typically we see that the uranium percentage removal decreased. Typically, again found no explanation, or people could not come up with an explanation. Again, keep in mind that this is for the amorphous ferric oxyhydroxide. So it could be that, let us say, the charge of the relevant compounds on the adsorbent or the uranium, let us say, could have changed maybe, but until we conduct a greater what do we say, or further detailed analysis, we cannot draw any conclusions about the basics or the principles affecting this particular behavior. But we do see that pH and what do we say, the relevant uranium removal are interrelated. Again, as pH starts decreasing again, right, I mean pH increased initially and then decreased, right, September to February 1998, and then again it decreased, and during decrease again typically we see that the percentage uranium removal increased again. That was the case here too for both the wells and the AFO, right. Again these are aspects that need to be looked at in greater detail later on, or you need to draw the conclusions from and go ahead. But for that obviously we need to understand, or try to sample the PRB material and see what is happening out there. And then again comparison of uranium concentration in filtered and unfiltered water samples. So why is this important? Again, what are we doing here? We are going to, let us say, you have the uranium contaminated groundwater passing through the PRB and leaving the system, and this water you are analyzing directly without filtering and once after filtering. So if there are any colloids or such, you are going to be able to see a difference. So typically with respect to zero valent iron or bone char, or these are the non-barrier samples. So non-barrier samples obviously they are right bang on the particular center line, right. But with respect to the amorphous case though, you see that they are above this particular line. What does that mean? That you have colloids being formed, let us say. What does that mean? That in unfiltered concentration is higher than the filtered concentration. That I am talking about the amorphous form here, right. So amorphous form, you see that the concentration of the relevant uranium in the unfiltered samples is greater than the concentration in the filtered samples, right. Let us say if I look at this data point, right, you see that slightly it is higher, I guess. So what seems to be the case? So looks like the relevant mechanism is leading to formation of mobile colloids, let us say, that are leaving the system, right. So obviously these colloids will be filtered out, that is why you see that the concentration in the filtered samples is lower, but in the unfiltered it is higher, that is what you see. So obviously this is something you do not want, as in you do not want your particular AFO or the PRB to be mobile, right, because again you are going to have transport of the uranium. But if you looking at the particular data, which I believe I am not presenting here though, is that this particular case, as in I have my PRB here, the AFO PRB and groundwater coming in, and so some of the colloids are leaving the system here, right. But because I have again the media out here, the subsurface media out here, the concentrations are not greatly different down the line though, as in these colloids are being entrapped in the relevant subsurface media though. But still this is something you need to be considered, because you do not want to have colloids that can be transported over greater distances, let us say, right. So again changes in pH values, again we are looking at the 3 barriers: phosphate, zero valent iron and AFO, and one, let us say, upstream, let us say. So this is the actual trend, upstream concentration, let us say, without treatment, yes. And for PO4 3 minus, which was primarily precipitation, this is what we observe, and for AFO this is what we observe, And for 0 valent iron though, we see that the concentration of the relevant water, treated water leaving the system, not concentration, pardon me, pH of the water leaving the system is pretty high, almost 3 pH units or 2.5 pH units compared to the system. What do we say, that is at 7, right? That is something to be concerned about. But let us try to understand the system or why that is coming about though, right. Again, keep in mind that for 0 valent iron, what is the what do we say process here that is involved? We have a reducing agent. What is that? Fe0, 0 valent iron. So, if any oxygen is present in the groundwater, as can be, right, oxygen is going to be reduced and you are going to have Fe2 plus and OH minus released. Obviously, when you have OH minus being released, what do you observe? You observe a increase in pH. Similarly, even in the case then when you have no oxygen or in anaerobic condition, 0 valent iron, what do we say, can reduce water to Fe2 plus and again you end up with some OH minus. So, that is what you see out here. Both when you have oxygen or even in the absence of oxygen, you see that OH minus is being released or H plus is being taken in, let us say, if you depending upon how you balance the reaction. And so, that is why you observe this particular change in pH. So, depending upon the issues with respect to pH change downstream, you can look at relevant remedial measures, but typically if you are trying to balance it between the uranium concentration removal, which is almost 100% in the 0 valent iron PRB, and the pH change by what we say 2.5 units, and again you are going to have dilution later, that should be, that is reasonable though, right. So, let us move on. So, again changes in dissolved oxygen concentration, what are we looking at? PO4 barrier, 0 valent iron, and the last one the AFO, I guess, right. So, let us look at the data sets here. So, obviously what would you expect, or for which case would you expect to have lesser 0 valent iron, not 0 valent iron, pardon me, dissolved oxygen concentrations downstream of the PRB, as in what am I asking here? So, this is my particular PRB material, groundwater is coming in and leaving the system. So, for which PRB will I have obviously lesser DO or dissolved oxygen in the particular downstream phase, I guess. Obviously, it will be for 0 valent iron. Why is that? Because 0 valent iron is a reducing agent, oxygen is an electron acceptor. 0 valent iron reducing agent, it donates electrons, and electron acceptor, which is oxygen, it accepts the electrons, and we looked at the relevant reaction. So, again let us look at the data here. As you can see here, this is the what we say legend for 0 valent iron, and you see dissolved oxygen concentration is below the detection limit. But after I think around 6 months or so, you see a slight increase in the effluent dissolved oxygen. That could be because, let us say, as we talked about in one of the cases when we are analyzing PRB, if you have precipitation build up over the 0 valent iron material, you will not have as much active surface area available for interaction, let us say, and thus your efficiency slightly decreases, and maybe that is the reason why we see some dissolved oxygen concentration leaving the PRB, 0 valent iron PRB, right, after around 6 months or so, right. But obviously for PO4 3 minus or such, I think it is varying according to the what do we say influent groundwater dissolved oxygen concentration, right. So, that is something to understand out here. And final case, ORP or oxidation reduction potential, right. What does this give you an idea? For example, in your labs you will have the ORP probes or such, right, oxidation reduction potential or redox potential. What does that give you an idea about? For example, depending on the reading, let us say, of that redox potential, let us say, you can understand, let us say, is the water relatively what do we say have reducing conditions or oxidizing conditions or such, right. So, again that is one way to understand. Obviously, in which case of the 3 PRBs would you what do we say expect to have reducing conditions or reduced species, let us say, in the case when the water passes through the reducing agent base PRB, which is the 0 valent iron. So, let us see that out here. So, for 0 valent iron PRB, you see that redox potential negative and pretty low. So, that means reduction potential. So, it can reduce the water or any other compound present in that. So, that is what you see out here, right. Redox potential is pretty low, right. Again reducing conditions prevail. So, reducing conditions prevail here, right. But that is not the case for the relevant AFO or PO4 based barriers, and obviously it has differing what do we say redox potentials. Again, you can also correlate this with the dissolved oxygen concentration that we observed earlier, right. So, moving on. So, we look at this particular case, changes in ferrous iron concentration. So one particular example before we wrap it up for today. So this is, we are looking at it for 0 valent iron PRB, so ferrous iron concentration. We have looked at pH, we looked at dissolved oxygen, we also looked at the redox potential. So redox potential, obviously, when would that be higher? We mean lower, obviously, when you have reducing conditions. Obviously for 0 valent iron PRB, we looked at that. So same case here, ferrous iron though, when will it be released? When Fe naught is oxidized to Fe2 plus. So as the contaminant comes in contact with 0 valent iron, or oxygen comes in contact, or water comes in contact with the 0 valent iron, let's say, it's going to be oxidized to Fe2 plus, and Fe2 plus is going to be released. So that's what we see here. So in the upgradient wells, right, and these are different months, obviously, the colors correspond to different months, different sampling dates. Upstream you see that the ferrous concentration is relatively low, but within the PRB, the wells within the PRB, what do you see? That the concentration is pretty high. But obviously the trend seems to be differing and such, right. Again, downstream concentration relatively low. We are going to look at this, but looks like I ran out of time, so I am going to end there. But keep in mind that what is the take home message here? Depending on the type of material that you used, we are what do we say, experiencing different downstream conditions, or even within the PRB, one of which is the 0 valent iron. But one aspect is, as you can see, different trend here even within the PRB, and this is something we are going to analyze maybe for a few minutes in the next session, and then move on to the relevant aspect, which is natural attenuation, I guess, right. What is natural attenuation about? I mean, I guess it is self-explanatory. So let's say you have a compound out there, let's say it's a reduced compound, let's say, that you spilled into the soil and it reached the groundwater. So reduced compound, so it can act as an electron donor, let's say, and you have oxygen, let's say, in groundwater, that's an electron acceptor, and you have microbes that obviously want to grow, right. And so depending upon the delta G values or the energy that they can get from promoting this reaction, you will have this particular reaction or the redox process, and then the degradation of this particular contaminant going through, right. So that's something I am referring to as natural attenuation. So once I wrap up this particular case study of PRB in the next session, maybe for 10 minutes, after 10 minutes, we are going to move on to looking at natural attenuation, I guess, right. And with that, I'll end today's session, and thank you.